Welcome to episode 2 of Tacit Talk. I'm your host, Connor Hookstra, and today with us we have our second guest, Marshall Lochbaum, creator of probably most well-known, the BQN language, but also two other languages which we might talk about today, the I programming language and the Singeli programming language, all of which I believe qualify as array languages. How you doing, Marshall?
Good.
And I think, we will start off. So I should mention, Marshall has been on the Arraycast, as well as Kai Schmidt, our last guest on episode 1. I think a couple years ago now. It must have been 2.5 years, plus or minus. And then I can't remember if you
That
recall.
was the first time I was on.
Yeah, the first time.
Yeah.
And do you recall at some point we were talking so much about BQN, we realized, why do we just keep on talking about BQN? We should just
Yeah.
invite this person
Well,
on.
I was on twice as a guest panelist, like for a series of two, and then the next time I was invited just to be a panelist. So
Yeah. And so Marshall's been a panelist ever since then. I actually don't remember the episode number, but it's been so long. I think it's got to be 2 years plus at this point. So I will link in the description those episodes. If you haven't gone and listened to those and you enjoy this, definitely go check those out because it's going to be a lot of the same stuff. But hopefully you'll be hearing some new stuff today. But so yeah, links will be in the description. How about we start with maybe just a brief overview of your path to array languages and at what point you decided you wanted to create your own? Because I know outside of BQN, and Singeli, you have a lot of experience with other array languages, specifically APL and J. So I'll throw it to you, and you can give us like a overview or mini history of how you got to basically wanting to create your own.
yeah. Well, so I started out with J. Um, it was Henry Ridge, who was fairly involved in the early J community. Was a teacher at my high school, and he ran math competitions. So of course I did all the math competitions, and I knew him through that. Um, Starting into my junior year, which is just coming up on 15 years ago now, he asked if I want to do a self-study course in programming. Um, and so the idea was he would teach me how to program in J, and I do some sort of a project in that. So I bought his book on J, and over the summer I pretty much learned J programming. I was able to write some simple. I mean, I think I did maybe some very basic simulation stuff, um, but I learned J code that way. Went through the school year doing all sorts of J programming, um, and so from there, I did start to learn other programming languages even that year because I know there was something that I wanted to do to use some minimization routines for, and for that I read numerical recipes in C, which, as you might guess, was had code in C, and so I had to learn enough to be able to read C at least. And I picked up Python as well at some point. Um, and I think this really set me on to learning about other languages because I knew these languages were much more popular than J. I mean, nobody I talked to had heard of J, and yet J was, clearly far superior to these languages. So I wondered what else is hiding out there, and how many undiscovered ideas are there? Um, and I mean, now I kind of have now that I really know these other languages, as opposed to just having encountered them, I recognize that in a lot of ways, J was actually worse. Um, so, like, yeah, J has all these array programming, this array programming capability that you'll only find in array languages. But it's also like it doesn't have things like lexical scoping or I mean, its object system is really weird. It's not really designed to be user friendly. So there's all sorts of stuff that would help you, organize your code and things and keep stuff maintainable that's not in J. But so at the time that I was starting to think about making my own programming language, I didn't really realize that, and I just thought, array programming was the way to go, um, and that so I should really, and I guess, well, actually, there was a specific realization that brought me to working on I, which was not the first. It wasn't the first thing that I did in designing programming languages, but it was the first named programming language that I made. So before that, it was just kind of toy interpreters to figure out, um, how do all these ideas work? How do I implement things? And I'd worked with stack-based languages a lot, and of course, these are very easy to implement because you don't really have to parse anything. I use this as a way to get familiar with other languages also. So I would say, well, I want to learn Scala, and then I would try to write an interpreter in Scala, and then I'd discover, well, this is really awful because of type erasure, which it inherits from Java, and I would say, well, I don't like Scala now. Um,
How many times would
no,
you say you've done that with different programming languages?
um, not a ton. I mean, somewhere around 5 different languages, maybe. I couldn't really say.
Okay.
Um, Definitely, I did some work with Haskell. Yeah, I don't remember what other languages I tried out. This was a long time ago.
Did you like
Um,
Haskell
well,
better or worse than Scala? Do you remember?
oh, definitely better.
Definitely better. Okay.
Yeah.
That's good to hear for the Haskell folks.
Yeah, I mean, I guess Scala is designed to be practical, but it really, and its usage has fallen off too, I think, as people realize this. It's like, it's not a good combination of object oriented and functional programming. It's like, it's, trying to implement functional programming while compromising everything to keep within the Java ecosystem. So you don't really
It's the worst of both
like,
worlds.
yeah, you have to understand Java programming in order to use it. And so you say, well, here's what I want in functional programming, and here's how I'd write it in the functional system. And now here are all the dumb Java considerations that I have to bring in to implement this program that sort of works like it might work in a functional language. Like, it's
Right.
very strange. But yeah, anyway, that was a short-lived project. But yeah, so when I got started on I, was actually uh, this was caused by reading about Haskell, um,
Really?
because I read about how functors work in Haskell, and I recognized two things in functors. I recognized, um, and so a functor is kind of a generalization of the idea of a container that you can map over. So the first thing that I recognized is the obvious thing, which is that arrays are functors because you can map over their elements. But the second thing I realized, or maybe not realized, but saw in Haskell, is that functions are functors over their result type. So you can say, I have a function and I want to map the function of adding one over this function. And the way that works is you compose so that you'll add one to the result. And this does the same thing as mapping over a container. Like, because you can say, well, if I mapped over an array, then and I'll just use a one-dimensional array for clarity. If I want to get index I, the element I of this array after mapping it, that would be equal to taking element I of the original array and adding one to it. And the same way, if I have my function that I've mapped the 1 plus over, then this is the same as taking the, well, and I want the value of this new function with argument I. This is the same as applying my original function to the argument I and then adding one by the definition of composition.
Right.
So I recognize that these two things, which at the time I considered my two favorite parts of J, which were so function rank, the idea that a function has this built-in rank that tells you how it maps over an array, an argument array, and also trains, I recognize that these two things were actually essentially could be generalized. So they were different facets of the same idea of saying that a function implicitly will map over an argument that's of a type that it doesn't that that you've that you specified that it doesn't handle the type. So you could say, well, I mean, the concept is just, you have an implicit domain that your function will handle, and for everything outside the domain, you map over it.
Right.
So that's the foundation of I. And so, yeah, it also, brought in a lot of other ideas about like combinators that I've been working on. So I knew the combinatory logic, the SKI calculus. And so I brought in the K combinator specifically. That's called K and I. So if you have, and we can talk about the syntax of I guess, but if you have if you write like A dot space B dot K, that's going to apply K to B first, and that creates your constant function. And then you apply that function to A, and that returns B, which is the constant thing. So that's, exactly taken from SKI, or, well, that is the K combinator,
Right.
in combinatory logic.
Well, I mean, this is kind of a side question, but how did you stumble across the combinatory logic and SKI combinator calculus? Was that just Wikipediaing around and at some point inevitably you just fall upon it, or it?
It was probably through looking at various programming languages, and I mean, I think eventually I got into learning about some esoteric programming languages, and SKI was pretty much the simplest thing. I mean, not necessarily the simplest thing in the number of components it has, but in terms of how simple it is to define.
Right.
It's pretty much the most basic Turing complete programming language you can have. I still think that. Of course, the K combinator in there is redundant, so actually SI is the most basic programming language.
I think it's I is the one that
is it I?
Is redundant. Yeah, so it's SKI.
Yeah, so it's SK.
And then someone discovered actually you can spell I in terms
with
of
a lot of S's.
Yeah. You do get nicer looking combinator spellings if you have the I, because if it's just the S and K, I think that's on one of the combinator sites.
Well, of course, if you have SK plus definition, then you can just define I. So
right. I'm not sure. Maybe this is a good time if you want, because at some point we discussed sharing the screen. So because following that example, it was A space dot space. I'm not sure if we want to show like the I GitHub repo for a sec while we talk about the I language. It might be easier for the watchers to follow along, but we will still try to keep this audio friendly for the folks that are.
All right. So
look at that.
Let's see if this works. So I don't really want the doc. I want to.
So yeah, we'll link this too in the show notes of the episode. This is the I language GitHub repo on Marshall's.
Well, it's shared, but it's not letting me click on it.
It just moved for me.
Oh, it's just not showing up immediately. Well, that was strange. All right.
So yeah, it looks like there's an examples directory inside the I language repo.
So here's some example I code.
So it kind of looks J/K-ish, ASCII symbols.
Yeah. The biggest difference is that it all runs left to right. And you've got parentheses for the ordering, but you've also got it's white space sensitive. So Um, the spaces force things to have lower precedence. So this part's going to be about, well, it'll evaluate first this and then this, um,
So this
and then this last group.
so this expression is 1 comma 2 comma 3 space plus dot r tilde asterisk space 2 comma 4 comma 1. So maybe walk us through, and we'll see if the audio only listener can hang on.
Yeah, well, I probably shouldn't go into too great of detail about it. So the 1 comma 2 comma 3 is a list. Comma is the function. And this is, I guess I'll start on the many grievances with I here. I don't think you should form lists using functions. I think they should have a dedicated notation, because if you have a list forming function, then you have to question what happens if the elements are themselves lists. So I think I took from J and made comma asymmetric, where if the left argument's a list, it'll keep appending to it. But if the right argument is always treated as an element. So, like, I mean, that's just not how anyone thinks of the comma. It's not a function that you want to use on its own. It's just confusing in a lot of ways. And actually, later down, you can see that the way I formats arrays is that it uses the semicolon as the first catenation and then comma after. And I mean, that's pretty error prone.
Interesting.
But so you've got these two lists and a tacit function in the middle. And so another thing about I is that every expression is composed of an odd number of tokens. Because
every expression in the language?
Yes.
Okay.
Because the only construct I has, the only syntactic construct, is infix function application. So if you want prefix function application, you use an infix function for that, because that's the only thing you could possibly use. And the infix function is spelled dot. So here you can see above here, there's 100.i, which is like APL's iota, that gives you the number 0 to 99. And so, yeah, the syntax is just dyadic functions and white space to determine precedence. And there are even some rules for what the precedence is when you start a new line. So the whole program new lines in various places, and it more or less works. I mean, this is not like, I guess it's a little surprising, how far this syntax stretches in terms of utility, but it's not really as nice as having, a dedicated way to write a function and to write like loops and stuff, or whatever you have. But it is very simple.
Right. And I think based on that explanation, I can almost make out the second expression, which is 10.i, clearly iota. Well, clearly just because you told me that .i is iota. and it's left to right. So that makes this, I think, the second array language after Jelly, Jelly that I know of. I can't remember if Nial is left to right. I still recall that being right to left.
I think Neil is mostly left to right. I mean, it's it's got kind of a more complicated syntax that does. I don't think it's like purely left to right.
Okay, yeah. So I of the languages that I type day to day, though, or not day to day, at least once a week. Jelly is the only other one that I know that is left to right. So anyways, you get iota, 0 to 9 inclusive, and then the percent equals 0. I'm gonna guess is that percent equals 0 forms a tacit function that, with the 3 as the right argument, forms an infix binary function that is going to be modulus 3 and equal to 0. So it's basically showing you which numbers are divisible by 3. And I actually did that without reading it above, and I think That's exactly what it says above, which maybe nobody will believe me, but so I guess
Well, no, it doesn't really spell it out.
well, I mean, it does say to
Yeah,
find which
I
numbers
think
are
I've gotten
divisible by 3.
a bit better at being very explicit in my documentation because
And so how does
when
the percent equals 0, how does that parse? Is that like the B1
so
combinator, aka applying a binary function first followed by a unary function?
um, well, I mean, I'll tell you how I already told you how it parses. Really, there's only one syntactic construct in I, um, and that is infix function application. Um, so this is just an infix function. It's equals applied to division and 0. Um, and the idea with I is that because equals its domain is numbers, uh, the when you pass it a function, it automatically forms a train. It maps over these functions. And actually, 0 is conceptually considered a function as well. It's considered the constant function 0. Um, so if you write like 2 equals 3, that will give you 1, but the conceptual justification for it is actually that um, the constant function, the train formed by 2 equals 3, um, if you applied this to an argument, well, 2 would return 2 and 3 would return 3, and then equals would compare those numbers and return 0. Um, so it's actually um, this overall function 2 equals 3, it's giving you 0 because um, because even as a train, like the equivalence works both on numbers and on functions. Um, when you form a train on constant functions, you get a constant function that is the result of that function. Which I mean, there are some issues with that. Like conceptually, it's fine, but of course, you have this issue with infinite recursion. Um, like if I tell you 2 and 3 are constant functions, then why am I saying you can clarify things by just applying to one argument? Because all that does is give you the constant function back. So it's the same issue as this floating array theory, which is that you have like you have a function that the only thing you really know about it is that it returns itself, and yet somehow out there it also has this identity that like if you have 2, I mean, yeah, it's a constant function that infinitely returns itself, but also it's the number 2. And I've kind of I mean, I guess I didn't even know about floating array theory when I designed this system. This was just based on J. But yeah, I've kind of turned against this because I don't think it really mathematically works that well. Like basically you're adding like the layer that you're, or maybe you just don't add anything by having, you know, this infinite tree of functions. It's like what's actually happening is that it's the number 2. So the way I would prefer to present this now is that, you know, it is just the number 2. But in contexts that require a function, it can be applied as a constant function. And that's how it's done in BQN, or described in BQN.
Interesting.
So, I mean, I think that, and you could say the same thing about numbers in BQN. Like if you need an array, it will turn it into a scalar array. But the number itself is not considered an array. So, I mean, that's just a little bit of soft typing, and I think that is much easier to justify because you don't have to come up with this whole infinite recursion framework that doesn't actually entirely make sense.
Right, right. Okay. And so I see
So,
the
but yeah, the upshot of that discussion was that that in I, trains and function application are not even, it's not like function application causes it to form a train or something. It's a train is just function application. So, and the same thing about mapping of arrays. It is just function application.
I mean, it does in one sense for the APL informed or dialogue APL informed. If my understanding of what you said is correct, it does eliminate the need to call certain forks like special forks, like AGH forks and stuff like that. Correct?
Yeah. And
Because that's
you
like
have the,
a special thing where one of the tines is an array, not a function, and therefore, it does something slightly differently. This model, although you said it's
yeah.
not
So
ideal
one
in
thing
certain
is you could
respects.
write modulus equals 0, or you could write 0 equals modulus. Um, those
Right.
are just the same thing because you don't, there's no syntactic difference between a value and a function. But you can also like there's no need to have like all you have to do for this is say the syntax treats everything as a function. You don't have to say the semantics treat everything as a function. You can still have different types in everything. Um, so if I were to redo something like I now, I would just say, well, yeah, the syntax is very simple. The only construct is function application. But that doesn't mean that everything's a function because the syntax doesn't have to be the same as the semantics.
Interesting. Although, so now I'm a bit confused though. You said that zero. I mean, I get the point where you're saying in dialog APL you can only have AGH forks where the left tine is an array. You can't do the same thing where the right tine is an array. But you also said that in the modulus equals 0 tacit expression when figuring out which numbers are divisible by 3, instead of spelling it percent equals 0, you could spell it percent 0 equals. What makes that
No, you
possible?
do 0 equals percent.
Or 0 equals, or, right, sorry. Okay, that makes sense then.
Yeah, so you just flip the arguments around.
Gotcha,
Um,
gotcha. Okay, that totally makes sense. Interesting. Very, very interesting.
and I mean, I guess it's worth saying that BQN, because it has a context-free grammar, which is another way of saying, I guess, that the syntax has to be decoupled from the semantics. Um, well, I mean, I guess you could do it without it, but it's natural to decouple the syntax from the semantics because the semantics are the context. And so if the grammar is context free, it doesn't know about the semantics.
Right.
In BQN, you can form an, I guess you'd call it an FGB train, where the right tine is a value or is an array, say. All you have to do is get the syntax to work out so that the array has a function role in the grammar. So one way to do that is to pass it to an operator that doesn't do anything, an operator that just returns its operand. Because in the syntax, the result of an operator is always considered a function. So then when you put it in a train, it'll parse like a function, even though its value is an array. Um,
Hmm.
so BQN lets you, it has all the semantics. You can form a train from anything, but the syntax is geared toward this particular use, like an APL.
Right, right. And I guess, well, so here's a question that popped into my head, seeing as we've been comparing it so much to dialog APL and BQN. Before we get to this next example that includes forks, when we use the word train here, do the trains that are possible? Like my guess is that the answer to this question is no, but we'll see if my intuition is correct or my understanding is correct. Are the trains that are possible in I a superset of the trains that are possible in a language like dialog APL and BQN? Specifically meaning that like we have 4 different trains per se, the 2 trains, the 3 trains, and then you can call them monadically and dyadically, and those correspond to phi 1, B, and B1. Is that what trains are in I, or can you can do that and more uh,
So
with?
you're asking whether it's a superset or a strict superset?
Is it well, I'm guessing that it's either identical or if it's
I
a superset, or maybe it's a different Venn
Yeah, I
diagram. And
think the capabilities are the same. It's
Okay.
It's only those APL trains that you can do. Well, except of course having the constant on the right time. So it's equal to the trains that you can form in BQN, but APL can't do all of those.
Okay. So
Um,
it's much closer, if not the same, as dialog APL and BQN versus Jelly, which doesn't really have trains. It has chains, but it has like a whole
yeah,
table of arity sequences that like match to different combinators. When we say
yeah.
train
Well,
here,
and I
we
don't want to do this sort of crazy matching thing, but it is worth saying that um, in this paper that I wrote up that discussed the this key concept of I, that trains and function rank are really the same thing.
mm-hmm.
There, I made a little interpreter in Haskell that had not I syntax, but it used Lisp syntax. And there, since a function can have any number of arguments, you can have trains that operate on any number of functions and then operate on any number of arguments. So each function is applied to all the arguments. Uh, and then then the last function is applied to all those results.
Interesting. So this is the idea that, like in the case of a monadic or a dyadic fork, you technically could have like triadic, quadratic, etc., however many arguments, and
Yeah. I mean, it's not a different concept at all. It's
right, yeah,
like we don't have it purely because of the syntax that forces us into these two argument functions,
exactly.
which I mean, it's good for understandability, I think, but I don't know. It's hard to say. There are a lot of trade offs.
Yeah.
So
I think Julia actually. So Julia has the compose operator, which is just the jot. And that is not just the unary function composition, the B combinator, and the B1 combinator as well, which is binary, then unary. It's also variadic. So you can pass it any number of arguments. It'll evaluate that, and then pass it to a unary function after. And I think actually the papers that these were
the
introduced.
left function has to be unary.
Exactly, exactly.
Yeah.
So it's a unary function with any arity function, and as long as you give it the right number of arguments, it evaluates it. And actually, so I think the phi combinator and the B combinator, when they were defined in like the 30s and 40s, like the papers that defined them actually had this general like phi and B subscript n, which like showed that it doesn't actually, you're not restricted to just a unary or a binary function. It can be whatever arity. But obviously, due to the constraints
Yeah.
of BQN and dialog APL and J for that matter, you can't implement
Well,
that.
the case with J is pretty interesting because, as far as I know, so for those who don't know, J has a different two train, which works like a hook. As far as I know, the general concept of like the unification of these trains was never really considered. It was just the idea is, well, here's this thing that works on three functions that we'd like to have. Um, and if we put this in the syntax, we'll kind of have a gap where, like, you could compose any number. And in I, of course, that I have that rule. There's always an odd number of tokens in an expression. Um, so in J, they said similarly, well, if you had any number of these forks, you could have you would get a meaning from any odd number of functions put together. But there's a gap at the even number. And so, I mean, it looks like they just picked another operation that they would kind of like to have and filled it in there. Um, and it doesn't really work out that well. Like it's not a convenient function to use in this way.
Nope.
And if you have the two kinds of trains that are actually derived from the general principle, then you have some nicer properties. Like an example that I remember from the array cast was if you're calling with two arguments, then if you have the new kind of train that appears in I and later APL and BQN, uh, if you have this, the right function will always get called on both these arguments. But if you have the train and hook thing, then in the to train, the right function only gets called on the right argument, and it gets called on both with the train form. So as you go between even and odd lengths, the meaning of the right function just flips back and forth. which is, I mean, some people would argue that the regular train syntax is confusing enough, or the new train syntax. Um, but that just adds confusion.
Interesting. I guess this sounds like a great opportunity to bring up the back hook, which I think just falls out of what you just said, right? It's because you can do the same thing with like AGH and FGB.
Yeah.
Uh, the way that you've
Let me
and
check
so I
that
guess
here.
we should note that the although you don't have two trains, so you have a always an odd
There's,
number, but you do have hook.
yeah. Um, well, yeah. So the reason that hook fits into this odd number framework is that, yeah, you have two functions that you want to use, and the way you combine them is with this explicit operator hook, which is H or capital H and I. There's two directions.
Oh, interesting. So that's what I was going to say. Is while you were
So
saying that, I was like, right, we have the hook and back hook, but how does that work? But they're explicit in the form of H or capital H, and H is
yeah, so it's a lot like having this dot for function application.
interesting. So it's a very intentional choice of putting this in. Um, and then one of the things I say about I all the time is it's the first language that, or even paper, or like any mention of the back hook, which is like the analog of the S combinator. Did that just like fall out of you wanting to have symmetric, the ability to do both, or had you thought even before you were implementing I that like there was um, a missing hook to the
Um,
hook that existed in J?
well, I mean, I probably only thought it in conjunction with programming language design. So it was I can't say if it was before or after I started working on I.
Mm.
But yeah, it felt pretty natural to me that there should be this symmetry. And also, you can see here that I've split up the binding an argument to a function, which in BQN that's actually the same as the hook, using this constant the constant function idea that a number applies as a constant function. But here I have B is for binding a number on the right, and capital B, which is there's one down here, and here I even bind capital B binds an argument on the left, um, and so here the how does it, so the left yeah the left argument to capital B is this train modulus equals 0, and the right argument is another operator lowercase b. So that's very higher ordered. Yeah, and before we move past this, maybe I can go over which um, all the stuff that from I that has eventually appeared in array languages, usually not really caused by being an I, but um, I can say what sort of stuff, um, what sort of considerations I brought up that weren't necessarily obvious to array language developers immediately. So I have another tab here. All right. So here is the end of the very nice timeline of APL primitives on the APL wiki,
Oh yeah, this is a very nice
which I
page.
yeah I was able to track down. Well, I mean maybe I've missed some languages that introduce things earlier than I realized, but I was able to track down an origin for every function, um, which I always felt was the most plausible, at least thing to popularize the function. So I appears in this a few times. First, it was the first language to do this two train system, and that's because I was thinking in terms of these functors and functional programming. Um, like in Haskell, where I'd gotten this from, the idea that you can apply a function to any number of functors is pretty natural. So I mean, I just picked that up. But you can also see that Roger Hui had written about this in 2006, So he said already at this time, I don't think this two train as hook thing really makes sense. If I were going to do this again, I would make hook into an operator, and I would make the two train be applying one function to another function, or composing. Um, Although I don't think he suggested having a symmetric hook. So um, that's the one thing that I can say was, um, I mean, and not necessarily that nobody's ever thought of it before, but it was the thing in I that I definitely didn't get from anyone else. That
A-
was
and I have
that was
searched
new to me.
through a lot of the combinatorial logic papers and textbooks and
Yeah.
have not seen any mention of a combinator that follows the backhook pattern. So yeah, I
So
would
yeah,
also say it's from
everybody
I.
agrees that, or the hook's not the same as S, is it?
The hook is S, yeah, but the thing that
It is.
it
So
make
nobody's thought of the symmetric
yeah,
counter S or whatever.
but the thing that's well, I don't want to say irritating, but for lack of a better word that's not coming to mind, the thing that's irritating about the S combinator in array languages, aka the hook and J, is that a lot of the binary infix functions that you end up wanting to use, probably the most common one is replicate or compress. You usually want to apply the unary function not to the right argument of your eventually being passed to a binary function, it's to the left almost always. And so a lot of the times
Yeah.
when you're trying to build up these tacit expressions because of the way you end up taking your binary function and then using a reflex, aka the swap combinator or the C combinator. And it would, like, if I had a choice, I would
Yeah, and
have
that's super common in J too.
yeah, yeah. And so, like, I wouldn't say all the times, every once in a while, and actually the most common times where you actually get to use the S combinator, aka the hook, is when the binary operation is associative. So it actually doesn't matter which one you're passing it to. If
Yeah.
it's like the equal sign or something like that, then that's when the S is useful. But when you have a non-associative function, it's almost always that you're applying something to generate a mask, and then you're using that mask to do something with your original list. And then you need what is the backhook in I, which you can spell in J with the binary function reflex inside of an S. Anyways,
Yeah.
it's very like
Well, it's not quite as bad when you only have one argument to the thing overall, which I think is probably one reason why this has never come up in combinatory logic. Because if you want the flipped S there, I mean, you're just gonna write S, and then the first argument is gonna be flipped. So you just have one function to add.
right,
Um, but if you have two arguments, then you have to flip the whole thing to swap them around, and then you use a hook to apply your function to the what used to be the left argument, and then your central function has to be swapped around to get it.
right.
Um, I remember I was in the habit of doing this in J, and at one point I wrote something with this on the J forum, and Roger complained about it. He said, I can't read this pattern. Just I don't remember what he probably suggested using a fork, but he was like, just don't write the two swaps. That's too confusing. And so eventually I found a better way that doesn't require, tumbling your head around this weird pattern.
Yeah. All right. Anyways, back to so the backhook from I has caused, actually not the backhook, the two train in I was the first time it was implemented and then later adopted in Dialog APL and
Yeah.
BQN. What
And I
else?
mean, I can certainly say like Roger did that in dialogue when I had no, like I didn't know what was happening in the APL world at all. I just used J. Um, so that was really added to APL independently.
Mhm.
It's not that it was added because it worked in I or anything like that.
Right.
Um, yeah, and so then there's the reverse compose. And then the last one you see that was added to dialogue in 2020 is the constant K combinator from I. So there's a um, and I don't think I was the one. I don't think Marshall was the one who suggested that added to dialogue. I think that was actually Adam's suggestion, and of course I was familiar with it from having used it in I. But then I decided to incorporate it in my proposal for a top and over. Um, so I was the one who put together the full proposal, but a top and over were in Sharp APL. What we did was just swapped the symbols around because we felt the smaller one was a better fit for a top. And then we added this constant operator to the proposal.
Yeah, I always forget that constant uh, is there. And every once in a while, I'll write something, and either you or someone else will be like, "Oh, you're missing an opportunity to use constant." I'm like, "Right, I forget," because it's now that means it corresponds to 3 combinators. It corresponds to the swap, which is C, the duplicate, which is W, and then also the constant, which is K. Um,
Yeah.
which is great. We love that. We love
Well,
that.
I mean, I think ultimately it's not really good that that. Well, actually, with constant, this is fine because like if you're treating an array as a constant function, then swapping the arguments, it's still the same constant function. So you actually can think about constant as being just the what C and W combinators, but it promotes an array to a function in this way. Um, but yeah, I mean stuff like a top and rank sharing the same glyph. I mean, we like it's dialogue has a pretty full keyboard, and if you want to add a new glyph to the keyboard, that's a whole huge process. So it made sense to start overloading the functionality, and it's not like there's really a anything that's going to be super useful applying rank with a function on the right. I mean, you can say, yeah, there's a function that computes the ranks from the arguments, but I mean, J and BQN have that, and I don't use it very much. Um, actually, I'm not even sure BQN has that, but I don't know about J. Um,
Interesting.
but yeah, so I mean, it's kind of convenient to have one glyph mean a lot of things, but when they're completely different, like rank and top, if you designed a language from starting from scratch, you really wouldn't do it that way.
Yeah, I mean, speaking of designing a language from scratch, I mean, this is probably we've spent way more time than I thought on I, but this has been fantastic because I've learned a ton of stuff. But yeah, maybe at this point we should transition to the language that you're actively developing and have been for a couple of years now, BQN. And if,
Singeli?
I mean, we can talk about Singeli too, but
I'm most active on Singeli now, by the way.
really, okay. Well, I mean,
Yeah. Well, I
maybe
mean, the thing about BQN is it's designed to be, this small, minimal, figure out what is the essence of APL. I can't, really say whether I'm successful or not, but in any case, I gave it my shot, and you end up with a very well, a pretty simple language. If we're talking about stuff like I and the SKI calculus, I mean, yeah, it's a lot more complicated than that. But at the end of the day, I mean, there's in terms of array programming, there's a limited set of primitives, and once you've got those all implemented, you're done. I'm still working on improving the performance of some things, and we do want to add system functions for various stuff. I think so. We got pointer objects for working with the foreign function interface out of the way. Another thing is to have like system functions for reading and writing from specific parts of a file, like streams that you can successively read parts of a file, things like that. But yeah, in terms of, I mean, definitely BQN as an array language, like the design is done. There's if I have something more to say, eventually I'll make a new language. I don't know whether I will or not, but I don't really treat BQN as any sort of research project now.
interesting. And so, I mean, we will definitely talk about BQN, but is the main goal with Singeli to develop it such that you can continue to improve the underlying performance of BQN, or do you have other goals with Singeli as well? So, and I guess maybe if you want, you can give high overviews of both BQN and Singeli for the people that are listening to this for the first time and haven't listened to any of the ArrayCast stuff and maybe don't know about BQN and the fact that Singeli is used to implement part of BQN.
Yeah, so I'll just do run through the rest of the history real quick. Um, so I was working on I from somewhere around 2012 to 2016, with large gaps in between. I was in college at that time, and so when I graduated college, I went to work for Dialogue. I did things in APL. Nothing. I didn't do a ton of language design there. I mean, because stuff just moves so slowly. Um, in 2020, I quit, and we had done a little bit of internal discussion in the young APLers group on, how would we rethink APL. So I said, well, I'm not working on APL anymore. So I guess this is what I've got to work on. Um, and I started, implementing this, and because I had a pretty good idea of what I wanted the ideas to look like. And I started implementing this, and once, so there was a fairly long period where I was still under contracted Dialogue after I turned in notice. There were a few months notice, and then once I was actually out of Dialogue, I went on the APL Orchard and said, uh, "Well, I'm no longer at Dialogue, and I'm working on this language." And actually, Zyma at that point immediately, it was like, um, within the hour, I think, said, "I want to work on this too," which was really great. And he's still working on it. And so actually CBQN, which is the main BQN implementation, is really his project. I just contribute some stuff. Um, so BQN I guess I said we were rethinking APL. The idea is to really consolidate the existing APL knowledge, and combine that with, good ideas here and there in the programming world that are pretty widely accepted. So um, of course, the lexical scoping and defins has already been incorporated into Dialogue, but being able to, I made that the only function type, and made some extensions to try to make it more usable, like their function headers and things like that. There's object-oriented programming as well, which was not in BQN initially, but I figured out, eventually I figured out a decent way to do like modules for code organization. So you would say a file defines a module. And then I figured out that this was actually pretty much identical to the concept of an object in object-oriented programming, so they could be used for both. So yeah, BQN is the trying to get at the essence of APL, but also give you access to other programming paradigms that I think are good fits to use with it. Yeah, and so then in the course of this, eventually Zyma gets tired. Well, I mean, I've never implemented on my own a decent BQN implementation. Uh,
I
what I
mean,
worked on,
I guess you don't need to if you've got someone that volunteers within the hour and says, "I want to work on this." And I mean, Zyma has, as you
yeah,
can see on the screen, their own implementations of APL, and I'm not sure if even other languages. I think is there a Zyma K as well? I'm not sure if there's a. I know
not yet.
not yet. I know that there's a. I want to say that there's a couple other languages or projects at least that I've seen. Isn't that's the one I'm
Oh,
thinking?
definitely lots of other projects.
There's the copy and paste formatter across languages that I have bookmarked.
Yeah, they're just called Paste.
Yeah, it's called paste.
And I use his chat client for discussions on Matrix too. So
yeah,
that's yeah, it's designed to have a user interface that's a lot like Stack Exchange chat,
hmm
and it's a lot. It's kind of less fluff and more content than other chat clients. So that's my style. So I use that.
So yes, I mean you probably would have implemented it on your own if you didn't have someone that was.
Oh yeah, definitely. Eventually. Yeah, I mean, so the first thing preventing me from making a decent BQN implementation was that um, when he started on it, like immediately, he worked on adapting Zyma APL, which is written in Java. to run BQN instead. And so that's Zyma BQN. And it was never completely compliant with the BQN spec. So, and it's drifted off, or there have been some minor additions to the BQN spec since CBQN started, and then so it's not it can still run like a whole lot of code, but there are one or two things that are different, or bits of syntax that it doesn't support, and it's not entirely unmaintained, but just some like some of the more complicated multidimensional primitive stuff is not implemented there.
Right.
What I did from the beginning was I was trying to do as much of the development in BQN as possible. So nominally, I was working on a JavaScript interpreter for BQN, which is what the website still runs. If you ever do much with it, you'll probably notice pretty quickly that it's very slow. And the reason for this is not purely that JavaScript is slow. Not even mostly that JavaScript is slow. The reason for this is that it's mostly written in BQN. So there's two parts to that. First, the compiler is all written in BQN, but actually, the same is true for CBQN, and that works fine there because the compiler is written in an array style. So it's pretty much as fast as your array primitive implementations are, and it can be at least so it has a large per compilation unit overhead, so per file or something like that. But it can compile a whole lot of source code very quickly. But then the second part is the runtime is implemented in BQN, so it's kind of iteratively built up from some very simple primitives. I have definitions of like, here's how to do a transpose using, actually, transpose is like the worst example that I could have picked because there's, I discovered whole new ways to implement transpose based on that transpose implementation being faster than the one in CBQN. But so it says, here's transpose implemented in terms of taking indices and multiplying them together and doing plus outer products and then finally doing a selection. This method is sometimes, as far as I know, the fastest way to do it, with some, like, you can make some modifications if you have lower level control. But yeah, it implements primitives in terms of the others. And in JavaScript, what you've got is like there's a function that does plus on two numbers, and then everything is built on top of that. So it's doing loops using a JavaScript function that does each, and then this function is being passed a JavaScript function, and that's just not a fast way to do things. So, and everything is done through interpreted BQN. So like the definition of even plus is defined using the depth operator, which in order to run is running a block function that has been compiled to a series of statements. So there's just a bunch of added overhead. But so this system was working pretty well. Well, it was working about as well as it is now, which is great, except in terms of performance. By the time Zyma started doing CBQN, so he just said, well, we need a decent implementation of this language, and he was a little more. He felt this need a little more pressingly than I did, I suppose, and he started working on an interpreter in C. And he was able to get off the ground very quickly because we had all these self-hosted implementations in BQN. So all you need is something that runs the bytecode, which is a bunch of instructions like, apply this function to two arguments. It's stack-based even. So it says, like load the variable at this lexical depth at this place in the frame. Load this constant function, apply the function, things like that. So just a series of instructions. You need something that can evaluate that. And then you need some very basic functions like adding two numbers or looping over an array to start your implementation. So
So I, I,
Yep.
I was going to ask, your first implementation that sounded like it was a mix of JavaScript and BQN. Was the motivation for that just because you wanted to uh, write? You said at one point you were trying to write as much of it as you could in BQN. Like, what was the main motivation for that kind of uh, implementation style?
It was portability, so that for exactly this reason, so that when you implement in another language, most of the work is already done. Um,
Okay.
and so this also enables you, like I think there's a little implementation in Julia that's not quite done. I mean, various other people have done embeddings in other languages. So what an embedding would enable you to do is, like if you have an embedding in Julia, you can pass it native Julia arrays, um, and then you can run BQN code on those. So that's you would get basically perfect interfacing between BQN and the host language, as opposed to the typical cross-language story, which is to move data across. You either use a native function interface or you serialize stuff. Basically, you have to know like what the data format is. Instead, if you implement BQN and Julia, you can say, well, my BQN plus function knows how to add Julia arrays by using the Julia native function. So it's really you can write BQN code that's fully standards compliant and everything, and have it executed by the Julia runtime, um, which is something that's not really. I guess it's not been used as much as I had hoped. Really, most people who are using BQN are using it either standalone or they're interfacing with the foreign function interface and stuff. So, I mean, that's still possible that there would be a nice embedded implementation and people would use that in this way, but it hasn't really been used a lot for that. But also, I knew, for the standalone implementation, having this self-hosted stuff is nice because you can get started quickly.
Are there docs online for? Because it sounds like there's been a number of, like you said, there's a Julia one. I mean, Zyma's responsible for two different, the Java one, the CBQN one. You've got your own. Is this just because people are curious and that they're trying to go and figure this out on their own, or is there some place that is someone's, there's a Scala developer listening because we mentioned it earlier, and they're thinking, "Wow, I'd love to go do this." Is there a place to point people out of where they can get started? Because it sounds like it's easier than for other languages. You're just kind of left on your own and you have to start from zero. Sounds like this is easier.
Yeah, so there is documentation on how I guess it's presented on as documentation on how the virtual machine works. Well, I mean, I think I considered the basic runtime as part of the virtual machine.
Mm-hmm.
So, all right, so let's switch to this other tab. Um, so first, I have the list of what has been implemented. There's a description. This is the running.html page on the BQN website. There's a description of how this whole system works. Um, and here's what has been implemented. So the C and the JavaScript ones are the main, are the um, are the kind of officially supported things. They're what me and Zyma have done. Oh yeah, the self-hosted in BQN is actually pretty nice because then I can, like, if I find a compiler bug, I can test it out in BQN.BQN, and if I fix it, all I need to do to test it to make sure it works is run BQN.BQN again, um, and on the code. So I change the compiler and run it. And because it's just running the compiler as a BQN script, it picks up all my changes immediately. So I can check if the compiler works and then compile it, then build the bytecode for JavaScript and C after that. And hopefully the fix will be the same in all these languages. I've never run into any issues with, I mean, the compiler is just BQN code, so and pretty simple BQN code at that. So it's all portable. Yeah, and then the rest of this is things that other people have implemented. So there's a Julia version. Um, there was CXBQN, which is GPU oriented. I think he pretty much gave up developing that. And there was also an attempt at doing a runtime in Rust that was also um, the author of that decided to actually. I mean, I think all the efforts there, which are the idea is to get it running in Erlang, really is the main goal. But that's all based on CBQN now.
Is the C++
So,
one, is that the one by Asher? Or is this a?
yeah, that's right.
I was gonna say if there's a
Yeah, who is a fellow YouTuber, I guess.
yeah, fellow YouTuber and Nvidian actually. Um,
Oh, really? Huh.
yeah, I did. Well, I guess he didn't used to work at Nvidia, but then one time he joined and he showed up in the Slack, and I was like, whoa, I didn't realize fellow YouTuber and array
V
language.
Asher mentally. This guy. Oh yeah, he did a video on the VM.
Yeah, there's a few videos. I'll link them in the show notes. He's got a YouTube channel, and I believe there's a few videos, not just on BQN, but a couple other array languages, and also just GPU videos in general. So if you're interested in this kind of stuff, I'm sure you'll be interested in those videos. Um, yeah.
Yeah, but so there are the BQN virtual machine or documentation page. So it describes what the output format of the compiler is. So yeah, it has this overall structure, which is split into a list of blocks that have some information about them. Um, and then you've got these instructions. There's like you have constant objects, and you have blocks, and then there's basic stack stuff. The stack all stays in order, so there's not even any stack reordering. Um, then you have, creating arrays, applying functions, applying operators, create train, um, that sort of stuff. I mean, there are a fair number of operations, but all of these are so simple if you have it's just a matter of having like a one modifier type implemented. Then the call function is like one or two lines of code.
Right.
Um, yeah, and this is the same instructions in a maybe more readable format where it says what they actually do. Um,
Interesting. Well, so we're at the 70-minute mark, and maybe what we should do is we'll leave Singeli for a follow-up episode, because I know that you had
yeah.
a screen with some BQN code, and maybe we'll spend the next 50 minutes or so chatting about BQN. What makes BQN different from? I mean, we've already chatted about it a bit when we were talking about I, and then we'll leave a few minutes for questions if folks want to answer them or ask them. I've noticed a few of you have asked questions.
Well, I think at least we shouldn't leave the rationale for Singeli hanging, because that's like the one part of the history that I didn't get to.
Okay, yeah. So maybe
Um,
maybe say that, and then we'll come back
so
to BQN.
yeah. Um, so Singeli does come out of this CBQN project. So CBQN is intended to be high performance. I think in like there's still some primitives that have pretty basic implementations, but I think you can say in nearly all cases it's going to be faster than dialogue, except some pretty specific like bit manipulation that I've run into. Um, whenever I mean, really, I've kind of stopped comparing performance against other languages because like dialogue and J just don't tell me much anymore. So and the way that we do this is in large part through Singeli, which is implemented in BQN is one interesting bit. And this is useful for getting the BQN build to work consistently, but not really useful for anybody else who wants to use Singeli. But yeah, so Singeli is a compiler from a language that's in really what I think of as a new paradigm that compiles to some very basic C that's really assembly like. actually, it doesn't even compile straight to C. It compiles to an intermediate representation that could be compiled to assembly, but instead it compiles it to C because the rest of our project's in C. So yeah, the main idea of how it works is that it really pulls a lot of the stuff you're doing to compile time. So you can think of it either as an interpreter that runs at compile time and happens to emit some code as the process of running. So it's in that sense, it's not really even compiling your code. It's just running your code and outputting the runtime operations that your code specifies. Um, and in another sense, you can think of it as a compiler with a very overdeveloped templating system or metaprogramming system um, that is, of course, Turing complete and is and can access anything that you have in the language. So it's got, I mean, it's sort of inspired by C++'s template system um, in the very loose sense of like trying to figure out how you would make this actually work like in a reasonable way, because the C++ template system is really not nice to use. I mean, I used it in dialogue a little for doing arithmetic operations. If you want to have something like be generic over a bunch of types, um, you pretty much can do anything with C++ templates, but it's like the way you write everything is completely different. So if you want to compare a type to another type, I mean, you can't say like, all right, I'm implementing this function. Here's the generic implementation, but for floats, I want a different implementation. Instead, you implement a template, and then you have a template specialization, which has a constraint that the type that it's acting on is a float, and then the specialization applies before the generic form. Um, so in Singeli, this is kind of freed up by treating this template system as its own programming language, and then the programming language, of course, has you can test things, and so the overall syntax, there's a connection at least. You can see how a Singeli generator corresponds to a C++ template, um, but the generator is just like everything that was in the way is removed, and you can see like the complete programming language that was hiding there that C++ tries to keep you from using. C++ programmers consider it a bad thing that their templates are Turing complete. And Singeli just exposes this to you and says, here's your whole compile time system. You do whatever you want with it, and we'll do our best to make it into a usable programming language. And that's kind of where the array programming comes in, because to my mind, the most usable paradigm for this interpreted programming is will incorporate array programming at least, and it's particularly so for various reasons. This compile time language is a purely functional language almost entirely. It's designed as a purely functional language. In any case, there are some sort of gaps, um, and so that means you have no mutable arrays, and you can't loop over an array. You can map over an array, but not loop and like change elements. So that's a context where array programming is particularly powerful.
And this came out of a desire to, I assume, slash kind of know, because we talked about this on a Raycast at one point, to generate efficient code that ends up being used in BQN, which is,
Yeah,
it sounds like you do have some amount of bootstrapping here, because BQN itself is used to write Singeli, and then Singeli is used to generate the code that,
bootstraps all the way down, man.
yeah. So yeah, I mean,
Yeah, so the whole build process, if I can get this organized, is so the the sources of BQN are you have the C code in CBQN that actually that defines enough to run the self-hosted interpreter. Um, and there's another sort of bootstrapping sequence that consists of some simplified compilers. So those have really simple syntax. And CBQN doesn't have a full BQN parser that's written in C, but it does have a really simple one that can run this simplified compiler. And then you can bootstrap up into through two intermediate compilers and finally build the bytecode for the full compiler. So that's there, so you can actually get the whole thing from the sources that we've written, as opposed to having to start with the BQN implementation. So you can build the compiler that way, and there's also the runtime and a few other components that are written in BQN. The formatter that prints an array, so it'll format, it'll handle all these issues with if you've got a nested array, you want to show each element and then show the whole thing in this outer enclosing structure with the rank and all that. So you've got all this compiler, runtime, formatter, bytecode. And that, like normally you just have that pre-compiled in a file. So then you can build a BQN interpreter with that. And everything is at least implemented in C, so you can build it all without Singeli. So on a normal build, it's going to build that, and that's your kind of baseline implementation. It's going to do some stuff really slow, but it doesn't really matter. And then that's able to run Singeli. So then you have the Singeli compiler, and that can compile your Singeli sources into C. And then with that, you have then everything is in C, and then you just compile it as a C project. Although also, for most of our build stuff, Zyma also wrote a build system in BQN that we much prefer to using Make, because Make is really, I mean, if you've worked with Make, you surely understand.
It's archaic to say the least. It does work for stuff, but it's a bit archaic.
Yeah. So this build system is better at doing incremental builds and parallelizing stuff and keeping track of dependencies. And even parsing your options that you pass in, like that's it can handle more sophisticated stuff.
Right.
So once there's the baseline BQN, you do build with Make, but Make will pass everything off to the build script in BQN once it's able to, so that you can do more complicated builds and build faster and have nicer output.
Interesting. That is quite the
Yeah. So it's heavily bootstrapped, and of course it's good to use your own language to have an idea of, in order to know whether your language works or not. And of course, this is something that I didn't do too much with I, and the result is that I is lacking many features that you would need to do proper programming with it.
right.
So yeah, I mean, I use BQN for enough stuff outside of BQN that I think we'd be all right anyway. But it does kind of drive. It does like force you to actually, finish the usability stuff if like even your build depends on the language. Um, and so yeah, then Singeli BQN is the main use case for Singeli now. But I mean, more and more, I think like this is just the way to do low level programming. If you, and there's a huge caveat to this, which is that I think hardly anyone needs to do actual low level programming. So I really don't like that, like the whole rise of Rust now has convinced people that you should be using a manually memory managed programming language for like anything, because it's just putting extra work on yourself for no reason. Like garbage collectors and all are fast and they work just fine. So, you know, if there's a project where speed is not like the main priority, like if I mean even if speed is eventually going to be a priority, like you should probably implement your thing in a level language first, and then start building components in a low-level programming language when you need to. Um, so really only a very small number of things need to have these specialized implementations. And I think what this kind of Rust phenomenon leads to is a lot of people are working in low level languages, but not actually doing low level programming. Um, so I mean, if you write everything with like streams and stuff, it's like, sure, now you're programming at a higher level, but one, you still have various constraints from the programming from the lower level language that are pushing on you. And two, you're not going to get lower level performance because you're not actually giving the language any information um, about how to implement things quickly.
This is an interesting hot take, and it's actually echoed by Richard Feldman, the creator of the Rock programming language. He's on record saying, and Rock is implemented primarily in Rust. And he says, if he could go back a couple years to when they started working on this, he does love Rust as a language, but the complexity that has been added to the project because of the borrow checker and having to be aware of your memory lifetimes and whatnot for the memory lifetime profiles that the Rock compiler has, you're not actually getting a ton. And he says it's like the amount that he spent fighting with that for something that doesn't actually have a complicated memory profile. He said now he would have rather done something in Zig because he still needs the performance, but it's actually not that hard if your memory lifetime profiles are simple enough to kind of safely do that in Zig. And Zig has not the borrow checker, but a lot of safety stuff, bounds checking, etc. And his take is he still thinks the language is great, but a lot of people are reaching it for it when it's not necessarily the best pick. But there's a lot of hype, around, like you said, the rise of Rust, this phenomenon, if you will. So it's interesting to hear you say that because it's not the first time I've heard that now.
Yeah, well, in that case, it's even different because that's like deciding between different low-level languages. I mean, I'm saying if you want Rust, like why not OCaml, which is I think it's kind of strange how little it's used, but like, I mean, there are all these great high-level languages that, and the functional programming languages typically have the useful concepts of Rust already. I mean, they've got all this type system and stuff. You can do all sorts of safety things, but you don't have. I mean, you don't have Rust's memory safety because it's just garbage collection. Like memory safety is a completely solved problem if you're not trying to get maximum performance through managing all the memory yourself.
Right.
And I mean, the cases where you need, like, even in low level programming, the cases where you need to manage all the memory yourself are not really that common. Like, in a lot of cases, you're still going to be bound by computations that you're doing on large segments of memory that you've allocated. So, I mean, in those cases, like, even Go would, I mean, maybe you'll be missing some faster operations. So maybe you'd want some kind of C# or Java thing.
Yeah.
But like, yeah, the memory management is not the main benefit of low level programming, I guess I can say.
Yeah. Well, I guess, yeah, you
Yeah.
made that point, but
Well,
you
and
were,
so
or go ahead.
to point out where Singeli fits in this, Singeli is I mean, all these new low level languages are trying to, bring safety to the low level paradigm. And I mean, I kind of think of that like the best way to be safe is to use a high level language, period. I mean, low level programming is like, even if you fix the memory safety issues, like it's just harder and that causes you to make mistakes. So if you're, I mean, it's valid in some cases to try to get, better performance with safety. And so Rust does have a place. Uh, but what Singeli is doing is instead it meets the low level paradigm where it is. It says the um, the requirement is that everything needs to correspond to something the CPU is able to do. So if statements correspond in an obvious way to branch instructions. Um, Other than that, I mean, the output of Singeli is really just branch instructions, um, specific operations that are like, for example, addition of two registers, things that the CPU can do in one instruction, um, and and setting registers. So set this register to this value. So everything you write in Singeli, once you get through all the compile time stuff, corresponds to a specific um, specific instructions to the CPU. And I mean, yeah, we don't force the programmer to allocate registers or anything. We do, and this is part of the reason to target C right now, is because we don't want to write a sophisticated optimizer. You would still want it to do things like do strength reductions on your multiplications. So like if you have a loop where you write I time, like looping over I and write I times K, you want to just add K to I at each iteration. Um, so we do rely on some optimization for simplifying the instructions that you're actually calling, but mostly Singeli is designed to actually tell the CPU to do, which I think, if you're serious about low-level programming, if you actually want to get the best performance, you need to be thinking about these specific instructions. And then what the value Singeli gives you is that it has this whole compile time layer on top of that, where you can write all the templates you want. And I mean, it's not, of course, you're still aware of low the low level layer, but it's like you're building your own abstraction on top of that. Um, and you can write, something that maybe takes two registers and swaps their values or something. So you can write all the abstractions that you would need in low level programming to make it convenient for yourself. Um, but at the same time, the way this corresponds to the low level operations is defined by evaluation of your code, and it's not defined by an optimizer trying to figure out what it is you want and how to accomplish it. Because if it gets your intentions wrong, you may as well be using a high level language.
And so, have in your benchmarking, to whatever extent you've done that, have you seen that this perform like this strategy, I guess you can call it, leads to like highly optimized, or not optimized, I guess is the wrong word, but just highly performant code?
Um, well, no, not at all. uh, it leads to the exact code that you wanted to write. So, like for any given function that we write in Singeli, we could do it easily enough in C. We can write, and a lot of what we want to do is vectorized code. So in C, this is really awkward. You use these vector intrinsics on vector types. So you could always write that out in C. I mean, you could essentially write the thing that the Singeli compiler outputs. What Singeli allows you to do is to write a whole bunch of related functions at once and very carefully control, which ones are doing what. So it allows you to take all the repetition and sort of underlying structure that if you're writing assembly, you would just have to repeat everything that you wanted to write. It allows you to pull that out, and instead like consolidate things so that you define the things you want. But it doesn't give you the performance. The performance is because you know exactly what assembly you want to run. You know your CPU, you know which instructions are available very well, and you know the right algorithm to use to implement your operation. So Singeli does nothing at all for you in terms of writing good algorithms. Um, but it gives you a framework for implementing these algorithms. In particular, if you, as we do in BQN, if you want to implement the same algorithm on many different types, um, it gives you the framework for doing that with less code. Um, and what that allows you to do is have very maintainable code that you can then, make one change and all your algorithms change. So it does allow you to test it much more easily and figure out, what works and what doesn't, what works on one type and what, like where you want to set thresholds for things. So it makes the process of developing these algorithms easier. But at the end of the day, um, you're just specifying what the CPU should do, and how good that code is depends on how good at the particular algorithms you want to do you are.
Well, I will say anecdotally that there's been a YouTube video on my list of YouTube videos to make since December when I was solving some Advent of Code stuff. And I solved it initially in Python. And I was surprised based on what the problem was, why it was, I don't know, it took a couple seconds or something. And I was like, it seems slow. And it was a array-based kind of question. So I quickly wrote the BQN solution and then spent another 10 minutes or 20 minutes trying to figure out how to profile it. And it was 2,500 times faster, like multiplicatively. I think.
Well,
Yeah.
that is a bigger difference than usual.
Yeah.
But,
So the name of the YouTube video that I haven't met that I plan to make is BQN is 2,500x faster than Python, and it's a clickbaity thing because it is
provocative
true.
title.
Yeah, it's true for my computer in this one little test case, but.
Make sure you check your Python code real carefully.
Yeah, but it does sound like you said, even though it's not necessarily doing anything for you algorithmically, this ability to test out different algorithms, generate all the code with much less handwriting of that code enables you to, I don't know, I guess, tune the algorithms that you're choosing, and then end up with faster code.
Yeah. Well, it doesn't make the code that you write faster, but it does make the process of writing it much faster. So
Right.
so you can cover more ground, implement more algorithms. You can do more sophisticated algorithms. Oftentimes there's something where, like, I don't know, maybe you have something that involves a loop over a variable, over like some number of machine words, say, like you've got a big Boolean array and you want to loop over the rows. So in that case, you've got some overhead from that loop. But sometimes you'll know ahead of time that you don't actually want to loop, that there's only exactly one row. And so that'll allow you to do things like pull these cases out. And most likely you can write the same code for both of these cases. And, maybe you'll have some compile time if statements to decide, to do one thing or the other at a particular place. But so without rewriting this algorithm or copying it, you can share the same algorithm, but have one version that's specialized for a shorter input, and one that's generic. And so then the specialized one will be faster. The generic case, if you've got at least 2 rows, it probably doesn't matter that much. Or maybe you want to specialize the 2 and 3 and 4 and then have the generic case after that. So in a lot of cases, writing more code will get you more performance, and there's no clear way to do it without that sort of specialization. Singeli makes that specialization easier, so you can apply more sophisticated algorithms and get that better performance while being more reliable, because you're writing less code, so there's less chance of errors. And so it's a better development process. It means you spend less time fixing bugs, less time, fighting templates, that sort of thing. And so it does, like, at the end of the day, the performance can only come from the programmer knowing what they want to do, but it makes it that much easier to implement.
Right.
Once you have the algorithm you want.
All right. Well, this is the first time. Usually, I think on
the
first
episode. I can tie it back into BQN, because the other thing that that's really useful when developing these BQN algorithms is this tool bench array that I built for benchmarking the different things, and that's all in BQN too. So what that'll do is you'll have a bunch of definitions of various like it'll say, I want to benchmark how fast is replicate, or yeah, maybe how fast is compress. And there's one that's based on like the type that you're compressing and also the density of the Boolean argument. So like if you have a density of 0, that means the result has length 0, so it should be finished pretty fast. It should sum that left argument and say, well, this result's empty. I know how to do that. Or if it sums to, if it's all 1, it should just copy the argument. So there's this BQN code to take this specification for what the benchmark is, and then it builds all these arguments and runs it, and at the end it produces a nice SVG graph, also using some BQN plotting, custom plotting things that's like suited for these particular kinds of ranges that I use. And so you get a really nice output that says, how fast is your primitive along all these important dimensions. And this is really nice for comparing different algorithms, because you can, open the old graph, build a new graph, and compare those two. And you can also see if there's two algorithms that you're deciding between. You can make a graph that's based on like what factor they depend on. Like for compress, there's some algorithms that are good at higher densities and some that are good at lower densities. And so you can choose a threshold and make your graph and see if there's a big discontinuity, like a jump where you've chosen the wrong algorithm. So when it switches over, the one of them is much faster than the other, and tune it so that they're more lined up. So yeah, array programming is actually very useful in benchmarking, which is also like benchmarking is just so important to improving performance, because you have to know how how fast your things run on the inputs you actually care about. So BQN makes it much easier to construct the inputs to your functions and nicely arrange the benchmarking results so that you can see how things perform and make decisions based on that.
And so bench array, is this specifically just for BQN, or can people use this for other languages / array languages?
Yeah, it's mainly for BQN. It has a cross-language tool, which is so this is a harder problem because when you're benchmarking just in BQN, that's a BQN program that calls BQN functions. So it's all in one language. It just works normally. When you're benchmarking across languages, you have some concerns like you have to transfer the data over somehow, or well, I guess you could generate in the target language, but then you have to make sure, like you're always wondering if the thing you generated is the same across languages. So either you've got to make a portable generator with all the random number stuff and have some sort of specification to make sure you're getting the same data, or you have to just serialize the data and send it through, which is what I've done. So I had this system that generates the same data in BQN that it would normally use to test. And instead of running it immediately, it writes it to a temporary file, and then it runs a program in the other language to read that file and run the program on it. That's kind of slow right now because it doesn't like it doesn't keep a running interpreter of the other language. It just restarts it for every new data set. So it's pretty slow, and the timings are a lot less reliable because, like again, the timing system that you want to use in BQN, I have all this fancy stuff that it does like one sample timing, figures out how long it expects it to take, and then it runs multiple runs based on that, and it decides how much data it wants to generate. You can't really go back and forth between languages with that, because you'd be saying, like you would have to, again, you have the problem of generating arrays. So if you're going to generate a fixed set of arrays. Um, then you can't, time it in the target language and say, well, actually, I wanted to generate this many arrays. Like, you could set it up, but it's just a lot more programming in the target language. And I wanted to keep the kind of footprint of that as minimal as possible so you can run it in another language easily. But so, yeah, I've got interfaces for J and dialog that just read the array, and they take in, how many times, what function you're running and how many times to run it. And it tries to translate the BQN functions into these languages so it has a comparable function to run. And you get timings out of that. So I can roughly compare BQN running to J and dialog. And I've tried to do this in the fairest way possible so the timings are actually comparable.
Right. That sounds quite powerful. Definitely, I'm going to take a look because I have some of my own profiling stuff, but I have not tried bench arrays. So we'll make sure to link it in both the YouTube description and the show notes for folks that want to take a look. We've gone over by 10 or 15 minutes at this point, but so I think probably what we'll do is we'll have you back to talk more about BQN itself, because we spent most of the time talking about the
I use the
overarching
most
stuff.
Tacit, so it makes sense that
Tacit
Talk would be.
Yeah, I'm super happy we got to talk about that because I did not know. I probably know the least about I of all the languages that are kind of that show
As
up
it
in
should
my.
be.
Yeah, I guess we didn't. I'm not sure if it was
Well,
explicitly mentioned either that it's not intended for use. It was an experimental language that you've stopped all
oh,
development on.
no, I mean, I was intended to be a usable language. It just wasn't.
It just didn't end up being.
I mean, I don't remember exactly what my thoughts on it, but I mean, I thought this was at least a promising area to explore. Um, and I think a lot of what I found out, like, I doesn't have variables, or it only has global variables, and the syntax for using them is not so nice, because they're accessed using basically strings of their names. So,
Right.
like, I found that, a lot of, and this was done, or at least the initial design was when I was not really all that familiar with kind of mainstream programming. I'd used it, but I didn't I didn't get all the ins and outs of lexical scoping and why that's a desirable way to arrange a program. I don't think I knew how a closure works. Um, so in a lot of ways, it's just it's an exploration of a particular paradigm that I thought, could be a really good way to structure your code. But I mean, now I think, it's sort of a curiosity. It's not, yeah, there are some neat ideas there, but like that alone is not enough for programming.
Right. Still interesting ideas explored, and it was great to chat about I. And so yeah, we'll make sure we link everything for folks if you do want to go check out I, or you want to check out BQN, or you want to check out Singeli, bench array. Last but not least, though, there were a couple questions. One of them, I believe, at one point was, when will this podcast be out on podcast apps? I believe Chris actually answered it in the chat, but for the audio listener, who I guess never saw the question in the first place,
They ought to know the answer.
this should be available on all platforms at this point in time. I definitely know it's on the big ones, Spotify, Apple, etc. So check your app; it should be there. One question was, what search terms should I use to learn about more about trains? I'm not sure. I know that someone mentioned
Which
going
kind
to.
of trades do you want to learn more about? If you want the ones that go on rails, it's actually really easy.
I'm imagining that he means tacit trains. I know that I linked to a ton of stuff in my combinatorylogic.com website, but I know you all, and some of those things linked to the APL wiki. I'm not sure. What would your recommendation, Marshall, be?
I think tacit programming is probably going to be the best term for that. Of course, that's more expansive than just trains, but I think most resources on trains would be connected to that. And yeah, there is an APL wiki page on trains, which I think is reasonably good about linking stuff,
Yeah.
in various paradigms and all that.
I'll say, too, that the very first paper, I believe, that Ken Iverson wrote didn't actually. I'm not sure if it uses the word trains, but it's entitled
Oh,
phrasal
so
forms.
yeah,
And I believe that was his initial terminology for what he ended up renaming trains. And I think the second paper he published on it was called Tacit Programming a couple years later. And then I think after that, it was the J Dictionary. That was the mid-90s. And that mentions trains a ton of times. But
Yeah,
yes.
well, I mean, there were some J things published before the whole dictionary, but I think that's about right.
I'm trying to think, was that the last question? I'm just scanning. A couple of people thanking Chris for answering the question. So yeah, I think that was the last question. All right. So with that, I guess we'll say thank you so much for taking the time, deep diving into I, and we'll have to have you back. And the plan is, folks, I mean, spoiler, but the plan is we're going to have a couple more guests on. Hopefully we're going to get Elias on for the CAP language. And then at some point I want to have a programming language implementer panel. So the goal is to get all the folks that have been on the first initial episodes, and then I'll basically kick my feet up and then let the implementers talk about implementing, because that's a podcast that I want to listen to. You can find them on YouTube sometimes. They have conferences. I know that there was like a NextLang Conf 2014 that had like Rust folks, D folks, C++ folks, and then they all just got up and were talking about implementing their languages. But I haven't really seen any panels like that since then. So that's the goal. Stay tuned, and be sure to check out the show notes to check out any of Marshall's languages, and tune into the next Arraycast where Marshall will, I believe, be there. And yeah, thanks so much for coming on, Marshall. This has been awesome.
So what's the Tacit Talk sign off? You just don't say anything?
Yeah, it hasn't been developed yet. We're
And
definitely.
with that, we will not say.
Perfect. All right. Thanks for watching, everybody.